Here I want to present to you guys an interesting proof that the number pi is irrational. And this is actually not my own doing, and I'm not sure how well known this proof is, but it's from Niven and it's from 1947, and the original paper is only a page long. Now we'll fill in a couple of details to make it a little bit more readable, but I've put a link to the paper in the description of this video. So we're going to use the following tool as we do this proof, and that is something like the generalized product rule. So here we have the product of two functions f and g, and we're taking the nth derivative. So we all know the product rule for taking the first derivative. Well, it turns out there's this Leibniz rule or product rule for an nth derivative as well, and here's how it goes. We have the sum as k goes from 0 to m of m choose k, the kth derivative of f times the m minus kth derivative of g. So it looks a lot like expanding a binomial, which is pretty interesting in itself. Okay, so let's get to proving this tool real quick. And we're going to use induction to prove this. And I want to point out that we could use the m equals 0 case as the base case, but that's just f times g equals f times g, where we have 0th derivatives everywhere. So I'm going to go ahead and use the m equals 1 case as the base case because it's a little bit more interesting. So let's go ahead and do that. So we have the base case is m equals 1. But now notice that means that we need to take the first derivative of f times g. But we know from calculus 1 that that is equal to f prime times g plus f times g prime. But we can rewrite that sum of two terms as the sum as k goes from 0 to 1 of 1 choose k, and then the kth derivative of f and the m minus kth derivative, or I should say the 1 minus kth derivative of g. This is exactly this over here, but writing it like that puts it in the form which is our final goal. Okay, so now let's make the induction hypothesis. So we want to suppose this is true for some m bigger than or equal to 1, and then we'll prove it for the m plus first case. So we're going to do that in the following way. So we've got f times g, the m plus first derivative, but now we can rewrite that as the derivative of the nth derivative of f times g. But now using the induction hypothesis, we can rewrite that as the derivative of the sum as k goes from 0 up to m of m choose k, and then the kth derivative of f and the m minus kth derivative of g. Now we'll use the fact that the derivative is a linear operator, so that means we can bring it inside the sum and inside that binomial coefficient, and apply just the normal product rule to this product of functions f, well, the kth derivative of f and the m minus kth derivative of g. So that's going to give us the following setup. We have the sum k equals 0 to m choose k, and then next we have the k plus first derivative of f and the m minus kth derivative of g plus the kth derivative of f and the m minus k plus first derivative of g. Okay, great. So now what I'll do is I'll maybe bring this part and this part to the top of the next board, and we'll continue on. So we're deep into the induction step of proving this tool that we will use to prove that pi is irrational, and right now we're at the following point. So we have the m plus first derivative of this product of two functions f and g is equal to the sum as k goes from 0 to m choose k, then the k plus first derivative of f times the m minus kth derivative of g, plus the kth derivative of f times the m plus first minus kth derivative of g. Now what we want to do is split this up into two sums, and so a sum of these terms and then a sum of these terms. So let's go ahead and get to that. So this is going to be equal to the sum k equals 0 to m. Now we have m choose k, the k plus first derivative of f and the m minus kth derivative of g. And then plus another sum, k equals 0 to m choose k, and then the kth derivative of f, and then the m plus first minus kth derivative of g. Now, if we look at this term right here, this has the form that we want, at least the derivative of f times the derivative of g does, in order to finish off our induction step. But we have the wrong binomial coefficient here, and our sum should end at m plus 1. So let's see if we can tweak that. And we can if we use this first term, but we have to re-index it first. So what we will do is we will replace k with k minus 1 and see what that does to us. So that is going to give us the sum as k goes from 1 to m plus 1. So let's talk our ways through that. So if k equals 0, and we change that to k minus 1, so we have k minus 1 equals 0, which means k equals 1. And then k minus 1 equals m means k is going to be m plus 1. And now we have m choose k minus 1, f the kth derivative, because we've replaced k with k minus 1, and then g is now the m plus first minus kth derivative. Great. But now we can add to that this sum as k goes from 0 to m of m choose k, and then this thing I'm just going to bring down. But if you look at this, now we have re-indexed this so that these terms look the same. So that means we can add them together if we are a little bit careful. Notice that we can just go ahead and add an m plus first term to this, because that will be m choose m plus 1, but m choose m plus 1 is 0. And then furthermore, we can add a 0th term to this, because m choose minus 1 is equal to 0, and that allows us to slam these two sums together. So now we have the sum k equals 0 to m plus 1 of m choose k minus 1 plus m choose k. And then we have these two blue underlined terms, so the kth derivative of f and the m plus first minus kth derivative of g. But now we'll use a binomial coefficient. This one is well known. That allows us to write this sum of two binomial coefficients as m plus 1 choose k. And now finishing all of this off, we have the sum as k goes from 0 to m plus 1, m plus 1 choose k of the kth derivative of f, and then the m plus first minus kth derivative of g. But that's exactly what we need to show in order to finish our induction step. And so we have proved that this tool is true. Now we'll jump into proving that pi is irrational. Now that we've proven our tool, we're going to prove that pi is irrational, and we're going to do this by way of contradiction. So in other words, we will suppose that pi is rational, but if it is rational, we can write it as a over b. I'll just go ahead and say that it's rational, where a and b are both natural numbers. So we know that pi is positive, which means it can be written as the quotient of two positive integers. Okay, great. And now the next thing that we want to do is a little bit tricky, and we won't really see the benefit until the very end. But what we want to do is choose some natural number n such that we have the following inequality. So it will be a to the 2n plus 1 over b to the n plus 1 times n factorial is less than 1. Well, so first of all, notice that this is definitely bigger than 0, so this, we want to choose n so that this is between 0 and 1. And you might say, well, how do we know that this is possible? And the way that we know that this is possible, loosely, is because the limit as n approaches infinity of a to the 2n plus 1 over b to the n plus 1 times n factorial equals 0. Essentially, what we have is like an exponential function divided by a factorial, but factorials always win when they're pitted against exponential functions. So winning in this case means that the denominator is dominating, and so this thing is tending towards 0. Okay, so now the next thing that we want to do is define a tricky function which involves a, b, and this number n that we have just brought into existence. And this function is the function p of x, and we're going to say that it is equal to x to the n, and then a minus b times x to the n, all over n factorial. So notice this is a polynomial of degree 2n. Okay, and now I'm actually going to make a claim about this. I want to claim that if we evaluate this at 0, we get an integer, and if we evaluate it at pi, which is equal to a over b, we also get an integer. But I don't have room to prove that, so I'll go ahead and bring this to the top and we'll do that. So on the last board, we got our proof set up. So towards a contradiction, we assumed that pi was a rational number. We called it a over b. And then because we knew something about limits, we were able to choose n so that a to the 2n plus 1 over b to the n plus 1 times n factorial was less than 1, strictly less than 1. Then next, we defined a polynomial p of x, which was equal to 1 over n factorial times x to the n times a minus b times x quantity to the n. Now I want to make the following claim. The nth derivative of p evaluated at 0 and pi is an integer for all values of m between 0 and 2n. So before we dive into the calculation of this proof, I first want to point out that we can use something about the polynomial in order to have a shortcut for a bunch of the values of m. So notice that 0 is an nth root of this polynomial, and pi, which is equal to a over b, is also an nth root of this polynomial. But then recall, if you know something is an nth root of a polynomial, then it's also a root of the derivative, the second derivative, up to the n minus first derivative. So let's summarize that in the following statement. And so because 0 and pi are both nth roots of this polynomial, we know the nth derivative of this polynomial evaluated at 0 and the nth derivative of this polynomial evaluated at pi is equal to 0, and this is going to be true for m between 0 and n minus 1. Okay, good. So that means we only need to consider the case when m is bigger than or equal to n. Great. Now what I want to do is think about this polynomial as the product of two functions. I'll call this one f and I'll call this one g, and then apply my generalized product rule to this. So let's go ahead and do that. So the nth derivative of p is going to be 1 over n factorial. I'll just use the constant multiple rule to bring that out. And then I have this sum of derivatives of f and g like we proved earlier. So we have the sum as k goes from 0 to m of m choose k. And then next we have the kth derivative of x to the n. And then we have the m minus kth derivative of a minus bx to the n. Great. So now, since these are power functions, we can actually easily write down their derivatives in general. So notice that this is going to be n times n minus 1 all the way down to n minus k plus 1 times x to the n minus k. But now we can rewrite that descending product using a binomial coefficient, and that's exactly what we want to do, just to add some more structure to it. So this looks a lot like n choose k times k factorial, and I'll go ahead and bring down this x to the n minus k. Okay, good. And now we can do something similar here. So notice this bit is going to be n times n minus 1 all the way down to n minus m plus k minus 1 times minus b to the m minus k times a minus b x to the n minus m plus k. I had to use the chain rule there, but that's okay. And now, similar to what we did before, we can collapse all of this into a binomial coefficient. And so this binomial coefficient will be n choose m minus k times m minus k factorial. Good. Now the next thing that I want to do is simplify this sum using these binomial coefficients, and I will split the sum into two parts. I'll split it into the part where k goes from 0 to n minus 1 plus the part where k goes from n up to m. Keeping in mind that we know m is bigger than or equal to n, so this right-hand part is not an empty sum. But I'll go ahead and do that on the top of the board here. Okay, on the last board we talked about the arbitrary derivative of this function p of x. So we took the nth derivative where m was bigger than or equal to n, and then I noted that we needed to split that into two parts via the sum. So we've got the sum as k goes from 0 to n minus 1, and we've got the sum as k goes from n to m. Now what I want to notice, if we evaluate this at 0, that this whole part cancels out, and that's because we have a factor of x in each of these terms. Then next, if we evaluate this at 0, we necessarily get an integer, because notice here we have the sum k equals n to m, making k factorial a multiple of n factorial. And the only thing keeping this from being an integer if you plug in 0 is this n factorial in the denominator. So let's go ahead and reiterate. If we have p, the nth derivative, evaluated at 0, this first term is 0. That's because the whole thing is a multiple of x. So if you plug in x equals 0, that's going to cancel out. And then plus, this next bit will most definitely be an integer, because in this range for k, we have k factorial is a multiple of n factorial, so that makes that thing a whole number. Okay, so now we need to talk through the other part. So now if we take the nth derivative and plug in pi, let's go ahead and recall that pi is equal to a over b under our assumption. But now plugging pi into this first sum, notice that we will always have an integer from this part, because the b in the denominator of pi will cancel the b that's out front here. So we're okay. And then furthermore, in this range, we have k going from 0 to n minus 1, which makes m minus k factorial a multiple of n factorial, which makes this bit also an integer. So in the end, we have the first term can be argued to be an integer, and then the second term is obviously equal to 0. But either way you have it, every derivative of this function p of x evaluated at 0 and pi is an integer. Okay, so now I'll clean this up and we'll move on to the rest of it. Now we've built up all of our parts and all of our tools, and we're finally in the home stretch. So the next thing that I want to do is define another function, and this is a function I'll call capital P of x, and it will be the sum as k goes from 0 up to n of minus 1 to the k, and then the 2kth derivative of little p of x. And now what I want to notice is that because of these values of derivatives of little p of x, that tells us that capital P evaluated at 0 and capital P evaluated at pi are both integers, which makes their sum also an integer. So that's really important to notice. Now the next thing that I want to do is notice that if we take the derivative of this seemingly odd combination of this capital P function, its derivative, and some trig functions, we have the following setup. So this is going to be p prime of x sine of x minus p of x cos of x. So this is in fact equal to little p of x evaluated at, multiplied by sine x. So I'll let you guys check that. That's surely just kind of a calculus 1 type thing to check. You need to be careful with this sum, but it's not too bad. Okay, great. But now by the fundamental theorem of calculus, what this tells us is that the definite integral from 0 to pi of little p of x times sine of x dx is going to be equal to p prime of x sine x minus p of x cos x evaluated from 0 to pi. Again, here we're just using FDC part 1. But now plugging in pi and 0 into this, we see that we'll get exactly p evaluated at 0 plus p evaluated at pi, which, like I said before, is an integer from this up here. Notice that plugging pi and 0 into this bit right here just gives us 0. That's why we have no p prime over there. Okay, great. Now the next thing that I want to do is do some bounding on this function right here. So we'll also notice that for all x on the interval 0 to pi, we have the following inequality. So we have 0 is less than or equal to p of x times sine of x, which is going to be less than or equal to p of x, given the fact that sine is between 0 to 1 on the interval 0 to pi. But now this is going to be strictly less than pi to the n times a to the n over n factorial. So let's talk our way through that. So notice that pi to the n represents the maximum of this function x to the n, and then a to the n represents the maximum of this function a minus b times x to the n, and those are both on this interval. So if we take the maximum of each of those component functions and multiply them, we definitely get an upper bound for the maximum of our given function. But now, using the fact that pi is equal to a over b, we can say that this is equal to a to the 2n over b to the n times n factorial. But now we can notice that this tells us that the integral from 0 to p of x times sine of x dx has to be strictly bigger than 0. So it's easy to check that it is strictly bigger than 0. But then it is going to be less than the integral from 0 to pi of this constant right here. So a to the 2n over b to the n factorial dx. But now, by simple calculus, this is equal to a to the 2n plus 1 over b to the n plus 1 times n factorial. Again, using the fact that we are assuming that pi is equal to a over b here. But now notice that we chose n before so that this was strictly less than 0. Now this may not seem like a problem, but we just showed a few minutes ago that this integral was equal to p of 0 times p of pi, which was equal to an integer by our big construction earlier. But what we have now is that the existence of an integer that is strictly bigger than 0 and strictly less than 1, which is obviously a contradiction. And what did it contradict? Well, the only big assumption that we made was that pi was a rational number. So we've achieved a contradiction, so that means pi is irrational. And that's a good place to stop.